Okay, so thanks to Raphael and Sanya for inviting me here, even though, as will become really obvious, if it's not already, I'm not a philosopher of biology. What I've noticed, though, from the talks here by real philosophers of biology is the interesting difference between philosophers of physics, which I am, and philosophers of biology, in that philosophers of biology are interested in the details of things, like cats. I'm interested in cats, too. I have a cat that I love, but I don't think of them in quite the same way that a paleontologist wants to think about cats. In fact, I hope he's doing well right now. Maybe I'll show you a picture at the end. The difference between the philosophers of biology is they look at things in detail, whereas philosophers of physics, those who are interested in foundations at any rate, like I am, look at things from a vast distance away in a very, very general and abstract way. Nevertheless, I noticed from the talks here that a number of the things I prepared to say make connections with things that have gone on here, particularly with Adrian's talk now and with Elliot's talk before. So let's see. I hope I say some things that will strike people here as very controversial and surprising. Surprising things that distinct talk. So here's some of the things I'm going to say a few words about, because these are big questions, and I'll touch on some of them and leave a lot unsaid. But I'm interested, one of my main interests is saying something about what the concept of scientific laws are, the history of that concept, the same about probabilities that occur in the sciences. And the question which has been discussed some in the, I don't know how interesting this question really is, but discussed some in the philosophy of biology literature is whether there are things that are properly called laws in biology. And I am very interested in whether there are objective probabilities that occur in biological laws and explanations, and how are biological laws and explanations related to laws and probabilities that occur in physics. And I'm especially interested in the relation between biology and statistical mechanics. Okay, so what's a law? Well, here's a list of conditions that people in philosophy of science throw up that you teach in the elementary course about what makes a generalization express a law. So one is that whatever laws are, they make true corresponding generalizations or equations, that they're components of systems of laws, that they're universal, they support counterfactuals, they play a certain role in explanations, and that they're confirmable. Sometimes this condition is added that they govern whatever they're doing. That's a controversial one because it depends on what exactly we meant by governing, and I'll say something about that in a while. The question about what's a law is asked in a nice way by Stephen Hawking. The expression that he said the way he asked the question is, what breathes fire into the equations? So here are three accounts of laws, these accounts of the metaphysics of laws, that if you encounter this literature at all, you know about these already. I'm going to mention them only because I'm going to tell you that I'm going to follow one of these lines, because I think it's the best account. But one account is a sort of what's called a governing account of laws. It says that laws, whatever they are, they're not just the generalizations, they're in some way parts of the universe that make the generalizations true. They govern the universe. In fact, this was sort of the idea that comes out of the origin of the notion of law in contemporary science, where Descartes and Boyle and maybe Newton had an idea somewhat connected to that in part. So that's one sort of idea. In contemporary philosophy, it's put forward, particularly by David Armstrong in his book, What's the Law of Nature. Michael Tooley has this idea. My friend Tim Maudlin has an idea like this. Another kind of account is the idea that, well, there really aren't laws that in some way separate from what they govern, which is what the first account says. It's rather that the fundamental quantities or properties of the universe come equipped with powers or with a disposition in some way. And that laws are certain regularities that result from the operation of these dispositions. So this is an account which Bird has, Ellis, and while Nancy Cartwright doesn't believe in laws, if she did, she would have a view like that. She definitely believes in powers. And then there's an account that comes from John Stuart Mill and Frank Ramsey, and especially developed by David Lewis, which is called the best system account. That's the account that I'm going to rely on in the discussion that I give here. It requires a lot more development in defense than I'm going to do here, but maybe some of that will come up in the discussion. The basic idea that Lewis had is this. Actually, let me tell you, although a few people in the audience I know have heard this story, I'm going to tell you now before, so I apologize to them. But once when I was giving a talk about these different accounts of laws, I told a story like this. You can think about these different accounts in terms of the question, what would God have to do to create the universe? So on the governing account, what God had to do is create the initial conditions, the initial physical state, and then create the laws. And the laws then did all the work involved in the universe. On the best system account of Lewis's, what God had to do was just create the universe, the block universe. And the laws are certain generalizations or equations that are part of the best summary, best in the sense of scientifically best. Lewis thought scientific best meant that they optimized simplicity and informativeness in characterizing the whole universe. So I told this story like that. It was at a place in Germany that I gave this talk, and it was reported in the German newspaper because unlike in the US, and I guess here too, at conferences they send journalists to conferences. Maybe journalists went to this one because there were some famous scientists at it also, famous physicists at it. Anyway, I saw in the newspaper there was a discussion of this conference, and my name was mentioned, but it was in German, and I didn't really understand it. So I took the newspaper back to Budapest, where my wife's family lives, and I gave it to her mother to tell me what was said. And she started reading it, and then she started laughing hysterically, because she said, it says here that the theologian Barry Loewer. Okay. So I don't mean it like that. Okay. So here's what Lewis's account is. So I already described it. Here are some problems with each of these accounts that need to be addressed in a long talk about the metaphysics of laws of nature. The problem with the governing account is that it's really very difficult to understand what these laws are and how they're supposed to do their governing. The problem with the dispositional account, which I think Cartwright takes seriously, which he sees, is that it really is not very it's not compatible with really the ways in which the fundamental physics thinks about the laws of nature. And naturally she's skeptical about doing such things. Because the fundamental features of the world, the fundamental laws don't really apply to quantities alone, they apply to the whole state of the universe. But the best system account, I think, fits quite well with contemporary physics. The trouble with it is that people who don't like it thinks that just because laws in some way are part of a summary of the events that occur, that makes them incapable of doing their explanatory work. I think that's a mistake. I'm not going to go on and address that issue right now. The other thing that people sometimes say about it, look, if the universe is just a block universe, one damn thing after another, then the fact that there are any laws at all, that is to say that the universe can be systematized, the system looks like a total coincidence, like an accident. That's also based on a mistake, that someone thinks that. But I say that now just so you think it later and you can make an objection to it. Okay, there are a number of accounts of probabilities that occur in the sciences. There's an epistemic account of probability. That probability is a measure of rational degree of belief in some way. That there's a frequency account of probability, so-called propensity account, and there's an account that goes along with David Lewis's best system account. That's the kind of account that I want you to think about, that I'll focus on. Lewis's account works like this. Lewis thinks of probability as something that's introduced into scientific language in order to better systematize the block universe. So just like a long sequence of, let's say, ones and zeros or heads and tails or whatever, it might be very difficult to systematize it in a simple way if it's very more complicated. But if you introduce a notion of probability, it might be such that you could say, give a lot of information about the sequence by saying it's a Bernoulli sequence with a probability of a half of from trial to trial. Okay, so that's the basic idea of Lewis's idea. I think this is one of the best ideas that anybody in the history of thought relating to the history of probability ever cooked up. I think that Lewis himself didn't appreciate just what a great idea this is, and maybe I'll give you some more reason to think it's good. So people who've developed this account are David Lewis, me to some extent, Greg Callender, Carl Hofer also. And it's a lot of sort of an interesting discussion in the philosophy of science or metaphysical foundations of science about arguing over these various different accounts. Oops, I had a few things. Oh, so maybe just a word or two about the other accounts. So here's some reasons why I don't think they're good to have. Oh, well, this is yet a fifth account, which Elliot Sober mentioned in his response to me in a question. That's the account of, I don't want to give an account. So we call that the no account, and it's, it really is not a good line to take, I think, if you want to understand how probabilities do their explanatory work. Okay, what about in biology? Well, here's one thing that Elliot Sober says, which I'm really totally on board with. I'm not sure I want to read the whole quote here. Is it readable from there? No, it should be readable. So he makes the point that biology is just probabilities are everywhere. And this has come up in a number of the talks already. The talk that Adrian just gave, and Elliot's talk, and other talks also. And it's right. And so the question comes up, what are those probabilities that occur within evolutionary biology and other parts? So probabilities that are used in paleontology. And in some way, the probabilities that are used in a way, they inform degrees of belief, but they're thought of in some way corresponding to what's in the world. So they're not just a particular paleontologist or particular biologist's degrees of belief. They're degrees of belief that are supposed to reflect something in reality. So Lewis's account gives an account of probabilities which are objective features of the world. They're not epistemic, but like all accounts of probability, really, whatever probabilities are, there should be something which guides belief. As I think Bishop Butler famously said that probabilities are the guide to life. So one of my big questions, which if I were a philosopher of biology, I would write about, is trying to understand what biological probabilities are. But I think I know the answer to that. I'm going to give you the answer to that as this talk goes along. See what you think about it. What about laws in biology? Well, like I said, not being a philosopher of biology, I looked at the Stanford Encyclopedia to find out what philosophy of biology was about. And I was soon sent to two interesting laws of biology. I guess I knew about these a little bit before. But one is a nice thing that McShay and Brandon have been arguing for in a book of theirs. They call ZEFL. I forget what it stands for, something like zero evolution, zero something.
Zero force evolutionary law.
Okay, I knew, of course, Alex being Colin to this, and that's what it is. So they liken this to Newton's first law, because their idea is that even if there's no natural selection going on, that there'll be an increase in diversity and complexity, just naturally, just because of random fluctuations, really. But they don't say much about where the random fluctuations come from, except a hint that maybe they think it's connected to statistical mechanics. That's right. And then there's the principle of natural selection. I'm not sure it can really be formulated literally in the form that we think of as a law, but basically the idea is it's a generalization which says something about how fitness, which itself is probabilistically characterized, is related to the to subsequent to the given the fitness of one generation, how it's related to subsequent generalizations. Anyway, the main point is that probabilities occur in all of those. So then I looked a little bit further, and I found an interesting paper by a couple of biologists called Travers and Saylor, and they're in San Diego, but I don't know much more about them. And they listed 3 laws of biology. And their absolute first law was really interesting to me. The first law was that all living organisms obey the laws of thermodynamics, as if they had any choice of the matter. And that reminded me of an episode of The Simpsons you may remember, in which, you remember the name of the Simpsons' little clever little girl, Lisa. And Lisa was always inventing things. And one time she came to her father and said, "I've invented a perpetual motion machine." And he said to her, "My dear, in this house we obey the laws of thermodynamics." Perpetual motion machines are conflicting with the second law of thermodynamics. Well, it depends which kind of perpetual motion machine she invented, but it's not so clear in the discussion. Anyway, there's a worry that people have had from the very beginning of the development of thermodynamics and evolutionary theory, and they kind of developed around the same time. But there seems to be a kind of prima facie conflict between the second law of thermodynamics, which says that something called entropy, more about that soon, will never decrease and will always increase, spontaneously increase in any isolated system, or more or less isolated system, and evolution, or even for that matter, the existence of life. In fact, from the point of view, the big picture, all the way far away from the details picture of the foundations of physics, if you think about things, if you just were told that the universe we're going to tell you about is a universe which has the fundamental ontology and laws of our universe, and among the laws are a law which underlies the second law of thermodynamics, you would be astonished to learn that there's anything alive in such a universe at first. I think that's right. And I found a nice expression of this by Stuart Kaufman, who I know has written popular things about this and I've read a bit about, but I don't know how seriously he's taken actually in the philosophy of biology community. But he does something like this: if all one knew about a universe is that its fundamental ontology consists of particles and fields and so on, conforming to dynamical laws and the second law of thermodynamics, one should be totally astonished to find anywhere in the universe life evolving so as to increase diversity and complexity. However, there's also the idea that it's the second law of thermodynamics in itself, that it's at the bottom of how it could be that there's life in the universe. So there's an interesting conflict for me. It's the reason that it seems to be a conflict is if you think of some ways in which entropy increases, like global warming is. So on Earth, of course, in all parts of the Earth, in systems of the Earth, entropy is increasing in some systems. Some systems keep entropy pretty low, like I hope as long as we stay alive here, our entropy stays relatively low. And so the second law of thermodynamics, or a corollary, according to the Sayer and Travers, is that when systems reach equilibrium, they're dead. Anyway, global warming is a picture of it. It will decrease complexity and diversity, of course. Okay, so what about the laws of thermodynamics? Well, I'm not going to give a tutorial on thermodynamics, but but underlying the laws of thermodynamics, in particular the second one that says that entropy increases, is the idea that all matter, or all systems for that matter, are composed of enormously small things that have many, many degrees of freedom. At some place, this comes to my mind, that Richard Feynman was asked, suppose all knowledge of physics was destroyed, what's the one thing you think should be passed on to whoever the successors was? And his answer was, it's that the world is made up of many degrees of freedom. And this is right, and it's a very profound matter. He said it atoms, but that's what he meant, as many degrees of freedom. Because of course atoms themselves are not something that's fundamental. Okay, so when thermodynamics was being developed in the 19th century, Ludwig Boltzmann in particular, but Boltzmann and Maxwell and some others, realized that they can give an account of thermodynamics. Thermodynamics deals with quantities like temperature, entropy, as I mentioned, heat, work, and so on. They can give an account of it in terms of the idea that that systems that it applied to are made up of many, many degrees of freedom. But in order to do that, they have to propose probability distributions over the microstates, or the degrees of freedom of a system. And they then showed how in the sense of giving sort of, not in the way of, not literal proofs, because proofs are very difficult to come by in this area, much too complicated. I have a friend who calls the kinds of proofs that are used in statistical mechanics Jewish proofs, because they go like this. You write down the conclusion on the board, and you say, why not? And they are something like that. Anyway, but they're better than that. And they're able to prove that for the universe as a whole, and for energetically isolated systems, entropy will never decrease, and typically increase. So what is entropy anyway? Well, the macro state of a system at a time is characterized by its thermodynamic quantities, and including volume, energy, temperature, pressure, mass, charge density, and so on. And there will be an enormous number of microstates, that is to say, particularly specification of what the positions of particles at those degrees of freedom, where they could be, what their momenta are, and so on, that are compatible with any particular macro state. So that's going to be a key idea for this talk, and probably one that pretty much everybody here knows, that when we talk about microstates, those are the fundamental, the distribution of fundamental quantities. For Newtonian classical mechanics, which is easiest to think about first, no difference really for anything I say, will depend on taking quantum mechanics seriously, is the positions and the momentum of the particles. And so for any macro state, that is, say, any particular specification of here's a system, here's the average density, and here's its temperature, here's the total energy, and so on, there'll be infinitely many microstates that realize are consistent with that state. And entropy was identified by Boltzmann with the logarithm of, in some sense, the number of microstates. But since it's infinite, you've got to choose a measure. But the basic idea is that lots of microstates that realize a macrostate, the entropy of the macrostate is the size of that macrostate. And this little equation that's on the board there, a definition by Boltzmann, was important enough, so he put it on his gravestone. Boltzmann is a very interesting character, and surely one of the great physicists ever. He became very depressed late in life and actually committed suicide near Trieste, a place that I've been at. It was very sad. I don't know why he became depressed, but it might have been because he was a real proponent of the atomic theory of matter. Everything was made up out of atoms. There's a kind of thermodynamics that I was just talking about, where statistical mechanics depended on that. And he was opposed by Ernst Mach a lot. They got into a lot of arguments. And Mach was a better arguer in certain respects. And so Boltzmann committed suicide, I think in like 1903 or 1902, something like that. And the crushing argument that for the existence of atoms came in 1905, although the evidence for it was available before, but the argument was given by Einstein, and this is what he won the Nobel Prize for, actually, for his account of Brownian motion. So the probability distribution, in fact, that Boltzmann introduced in order to give an account of entropy and the laws of thermodynamics, that probability distribution is also the same probability distribution that gives an account for Brownian motion. So the second law is probabilistic, and maybe this little picture may give you an idea about it. The little figure in there is supposed to be Maxwell's demon. This argument was given by Maxwell and the other great physicists in the 19th century. If you imagine a bunch of particles moving around, and let's say some are red and some are blue, and suppose that the system started out with all the red ones on one side and all the blue ones on the other side. So that would be a system with relatively low entropy, okay? Because there are not that many configurations of the particles, in which they're all red on one side and blue on the other side. In fact, there's just one blue. Okay. But if they're moving around, it's kind of randomish motion, which is what the probability distribution that Boltzmann introduced corresponds to. Then if there was a little demon there opening and shutting the door randomly, then after a while, some of the blue ones would go over to the one side and the red ones on the other side, and they go back and forth. And after a long enough time, you'd get a mixture. You'd get I don't know what happens if you mix blue paint and red paint. What do you get? Purple. It looked the whole thing looks like purple. Okay. And here's another little illustration of how the second law of thermodynamics works, how entropy is increasing. Think about an ice cube, all of the atoms, the degrees of freedom of an ice cube, they're moving around, they have certain momenta, certain positions, they're moving around in a certain way, banging into each other, and it's because of that, and they're banging in with the warmer air, I'm assuming the air is warm, that after a while, the energy is transferred between the air and the molecules in the ice cube, and in a while you get a puddle of water. So that illustrates how the second law works. Here's another little illustration which should give you a good idea. So as I pointed out with the example of the Maxwell-Lehman picture, entropy states are very small states. So the number of states, so to speak, or the measure of the states, of the set of states which have low entropy is very, very tiny. So if a system started out in a very low entropy state and was just sort of wandering around, and think it was a random walk, which also sort of corresponds to the probability distribution that Boltzmann introduced, then you'd expect it to wander into higher entropy, bigger volume states. And in fact, that's what happens, and what the second law says will happen. Okay, so there are a bunch of apparent incompatibilities between biology and thermodynamics. I kind of indicated them before. The one that occurred that pretty much everybody knows about right at the very beginning of when Darwin's views became known. And that was, and I think Darwin really worried about this. Some philosophers of biology probably know more about the details than I do. And that was that Kelvin, who's one of the developers of thermodynamics, said that Darwin couldn't be right, because Darwin said something like, for vertebrates to have evolved would have taken a few 100 million years, and Darwin calculated that the age of the sun could be no more than 80 million years or something like that. And the age of the Earth, he thought, could be no more, and it could either be less than that. And so Darwin couldn't be right. And of course, what was wrong here, in this case, biology beat out physics, because Kelvin was just wrong. We didn't know about the source of energy of the sun, or the Earth, for that matter, for them too. Another apparent incompatibility, which you often hear if you go to debate creationists, which I know something that Alex has been involved in a bit, and somehow I got myself into doing something like this last month. I don't know why I agreed to do it, but at any rate, you hear an argument that goes like this: look, the second law of thermodynamics is incompatible with the fact that living organisms maintain or even lower their entropy as they grow, and that they grow increasingly complex. This is said. The conclusion from this should be, well, there's no life, maybe, because the second law is true. Well, the conclusion should be the second law isn't true. I don't know why the conclusion of this argument is supposed to be, so God created life, but they think that. But you can see that there is a prima facie conflict between the second law and the increase in diversity and complexity. And it's also argued, as I pointed out before, the Kaufman's argument, that it's very unlikely that the random motion of atoms and fields will result in the formation of the first living organisms, and that they have the features that are required for reproduction and variation and so on. Though in fact, if the universe lasts long enough and is big enough, it's pretty much inevitable, for the kinds of reasons connected to ones that Werner mentioned, involving aircodicity, that at some point the configuration will correspond to living organisms. In fact, before that happens, more likely it is that things called Boltzmann brains form. Anybody ever hear about those here? I won't give you nightmares to talk about them. Okay. Well, all these objections are based on misunderstandings of entropy in the second law. What the second law says, it doesn't say that the entropy of the system never decreases. Of course not. How would your refrigerator work then? What it says is that the entropy of an energetically isolated system very likely increases, never decreases. But living creatures, the biosphere in general, is not energetically isolated. The biosphere is getting low entropy energy, radiation from the sun. That entropy, that radiation comes in certain wavelengths of radiation, which and organized in a way that's very low entropy. And in fact, what happens on Earth is that living organisms, mostly plants and bacteria, I guess, and so on, plants and make use of this, and then animal life afterwards, to produce a lot of entropy. In fact, that's what we are. If you think about human beings, we're just nature's way of producing entropy, dissipating heat. Not just by giving lectures on this subject. Okay. What about increasing entropy leads to increasing disorder? So this is a misunderstanding too. In fact, a nice example in which entropy increases, even though complexity or order also increases, is given by this kind of example, familiar to people who take thermodynamics courses. If you were to mix up, let's say salad oil and water, and shake it up a bit, you actually produce, by shaking it up, a lower entropy state. And entropy will increase as the oil and the water separate. And that's because literally there are many more configurations of the compatible with the kinds of the potential energy in the oil in that system, in which the oil and water are separated from each other, knowing they're all mixed up with each other, even though that may strike you as counterintuitive. So increase in entropy results in an decrease in complexity. No, it may increase, as I just said. And here's a nice example of this. Think about dropping some ink into water. When you drop a little blob of ink into water, the entropy of that system is relatively low. All of the ink is contained within a small spot. But as the ink spreads in the water, you get very complicated system. Little fingers of ink go out. That increases in complexity. Of course, that goes to a limit where complexity gets to the maximum, and then after that, complexity will decrease. In fact, our universe is very likely like that. So here are just some pictures illustrating some of the points I was just making. The sun gives us, it's been estimated, something like 20 low entropy, not low energy, but low entropy photons for each high entropy photon. No, what I say on the board here is correct, but on the slide is correct. But the idea is that the entropy that comes from radiation of the sun is much lower than the entropy that's dissipated. This is just a picture illustrating that order can be go along with increasing entropy. And in fact, one of the ways, most of the entropy in our universe is actually contained in black holes. So the idea that there's gravitational entropy, that was already present pretty early on in the development of general relativity, but was really made a lot of by Stephen Hawking later. And it turns out that black holes, Hawking actually figured this out, black holes are the repositories of enormous amounts of entropy. When the universe began, it was actually in a relatively low entropy state, as I'll emphasize it a little more in a minute. What the reason is that as matter attracted each other in the early universe, entropy was increasing while matter clumped together, and that continues until black holes are formed. And that's often said to be the fate of at least our epoch of the universe, is for it to be full of black holes until they radiate themselves. Okay, so that's that. Here's an interesting question, though, just to go take away from my talk, to figure out exactly what the relationship between increasing entropy and increasing complexity is. And there are some people who think that maybe another law of thermodynamics is needed in order to characterize the world and what happens in systems so that entropy increases typically in ways that also at first increases complexity until maximum complexity is reached, and then complexity decreases. I don't think that that's so, but it's an interesting discussion. Okay, so thermodynamics, in fact, despite what Kelvin said, is really compatible with life and with natural selection. And in fact, for this I'm really grateful to being invited to this conference, because I never read Schrödinger's great book, What is Life, prior to thinking about what to talk about here. And I assume that every philosopher of biology has read this over and over and over again. At least they should have, if they haven't. So the physicist, Erwin Schrödinger, one of the inventors of quantum mechanics, at one point gave some lectures trying to characterize what life is. And he saw right away that he'd have to make a connection between the second law of thermodynamics and the development of life. And what he saw then is that one of the main features of life, the characterization in general about what life is that what living organisms do is they take in energy, low entropy energy, and they use it in some way to keep their entropy relatively low. Now, how do we do that? Well, we do that if we're plants, by staying in the sun. If we're animals, by eating other plants or animals. Metabolism is a way in which, eating is a way in which so the term that's used actually is harvest low entropy energy and then dissipate it by giving talks and heating up our environment. So Schrödinger comes up with a general characterization of what living things are, and central to it is this feature. Now the question is, how do systems like that arise? Why do they exist in our universe even? Okay. So it turns out that under certain conditions, a system can evolve into higher entropy if it's interacting with the rest of the world. It evolves into higher entropy by dividing into subsystems, where one subsystem keeps its entropy very low, while the other part has entropy increasing. And this is an idea that's been developed by some biophysicists, and to my delight and amazement, I discovered that Alex suggested this in a paper of his. From talking to him, I don't know where he got this idea from. He told me he got it out of his mind. But it's a really good... What?
Now you're making fun of my talk.
But it's a really good idea, though it's been only a little bit developed. And one of the people who developed it, and it's curious whether people have heard of this biophysicist, a guy called Jeremy England. He's done a lot of press lately. He was declared in one article in Nautilus and some other science magazine as being the next Darwin. That seems to me to be an overstatement from my knowledge. I've only read a few of his papers, and I've emailed him with him a little bit. But he has an account of the origin of life, in which he doesn't have a literary account of, doesn't quite get the living organisms which are reproducing, or any mechanism for reproducing, like the way via DNA. But what he has shown is that under very general conditions, systems will evolve a kind of adaptation, which is a non-natural selection adaptation. They will evolve or change, rather, the better word to use, so that they increase their entropy by absorbing the radiation around them, absorbing the entropy, the low entropy energy around them in a better, more optimal way, in a better way. And so they actually change in a way that looks sort of like adaptation. It looks like they're adapting. It looks like they've been put together in order to harvest the free energy around them better. So one other thing you might take away from this talk is to go look up Jeremy England and see what you think about his ideas. Okay, so there's a big problem in the foundations of statistical mechanics. I didn't go into any details about what the probability distribution is that underlies the second law and all of thermodynamics. But it's the simplest one you can think of. It's the probability distribution that assigns equal probability to each microstate compatible with the system's with the universe's macrostate. So So imagining that the universe as a whole has something like a macro state, which means something like it's the heat, the temperature, the density of matter, the average frequency of radiation in small regions of the universe, small but finite regions of the universe. That's its macro state. And the right probability distribution that gets the second law out of it and the other laws of thermodynamics is the probability distribution that says that every microstate compatible with that macro state is equally likely. But there's a big problem with this, and when Boltzmann first suggested his account of thermodynamics, in terms of this probability distribution, it was pointed out to him by his assistant, a guy called Schuster, and a little bit later by Zermelo of set theory frame, that in fact, while it's this probability distribution together with the dynamical laws of classical mechanics, if that's the way he was thinking about things, does imply that the entropy of the universe will increase. In fact, what it implies is that it's very, very, very likely at any point that the entropy will increase towards what we think of as the future. It also implies that it's very likely that the entropy was greater in the past. And if you applied this to small systems, like let's say the ice cube, what it would mean is that if you came upon an ice cube that was half melted, sitting in this kitchen, and imagine this sort of isolated from the rest of it, energetically isolated from everything else, then while the Boltzmann probability distribution would imply that it's very likely that the ice cube will melt, it'll also imply that it's very likely that it was more melted than what we think of as the past. And of course, that's ridiculous. So something is wrong there. So Boltzmann struggled with this a lot. I don't think this was the reason he committed suicide. I'm not sure about that. And there is a solution to it. He sort of had the solution in a way, but he didn't quite present it. Later, Eddington sort of mentions it. Richard Feynman clearly states it in a great series of lectures he wrote called Character of Physical Law. And it was put in very clear form. It's become the matter of a lot of discussion in the philosophical foundation of physics now by my friend David Albert, who was the guy who talked about Jewish proofs we mentioned before. And something called the past hypothesis. What the past hypothesis says is that the macro state of the universe 13.73 billion years ago was one of very, very, very low entropy. Really low entropy. Mind-bogglingly low entropy. Now, in fact, cosmology points in the same direction. And this idea is pretty much accepted by cosmologists. Okay? And it's enough, together with the Boltzmann probability distribution, to get all of the laws of thermodynamics holding for the whole history of the universe. So it overcomes this objection, the so-called reversibility objection that I mentioned that would come if you just had Boltzmann's probability. Here's a little picture taken from a book by Roger Penrose. He was making this point too. And it's a picture of the creator. Again, don't misunderstand me. I'm not thinking that the creator looked anything like this. The creator picking out the microstate, picking out the macro state of the universe from all this enormous number of possible macro states he could have picked out. And has to be very careful because he's picking out a very, very low entropy macro state to start the universe off in. And once he's picked out such a low state, then for the whole history of the universe, entropy very, very, at any point, very, very likely increases. The very likely there is like a trillion likelies, trillion varies before the likely, more than a trillion really. In fact, Penrose calculated that if you just use the Boltzmann probability distribution, the probability of the creator, if he was blindfolded, just picking a state like this, the probability of his getting, on the Boltzmann probability distribution, the probability of getting a macro state of that size is 1 over 10 to the 120 to the, incredibly small number. Okay, finite, but very, very tiny. And that's led some people to think that this means that the universe is very fine-tuned with respect to its entropy. That's a whole other discussion. It's a mistake, but it's interesting topics to think. Okay, so why was the entropy so low at the beginning of the universe? Well, I already gave an indication of that. It comes from the fact that there's, because of the degrees of freedom involved in gravity and general relativity. Okay, Now to the main thing I want to tell you about. Okay. So the main thrust of my talk was, there's all these probabilities in biology, maybe there are laws of biology too. Where do they come from? Well, someone might think that the laws of biology or the probabilities of biology, they just come because they're independent, they're autonomous. When God created, the universe, he not only made the laws of physics, he also said, I will make these laws of biology. And then they may, if they conflict with physics, screw physics. I might have said that. Philip Kitcher sometimes writes as though that's what he thinks. Screw him. Sorry. I don't think he really thinks that, but he does. But people in philosophy of biology have struggled a lot to come up with some account, and this came up here already. They want to give autonomy of a certain sort to biology. And of course there is an incredible epistemological autonomy and autonomy from scale, but from physics. But when it comes right down to it, I'm going to claim that all of the probabilities in biology and everywhere, on the gaming table, in Trump's casinos, everywhere, they all come from statistical mechanics. A way of formulating this has been produced and has been argued for it now by, really first by David Albert that I mentioned before, and me. It was me who made a little observation about David's account. He did most of the heavy lifting, and I just made an observation about it. That we've been giving the name of limitaculous. I know a few people in the audience, because I told them, knows where this term comes from, but a lot of people don't, so I'll tell you. There's a Coen Brothers movie called Serious Man that some of you may have seen. In that movie, there's a minor character who never gets out of his pajamas and is just scribbling in a book. So you might think at first he's just a nerdy philosopher like we are, but it turns out he's much worse off than we are. He just never does anything. Someone asks him, what are you doing? And he says he's composing the mentaculus. And the person looks at him and says, what's that? He says, it's a probability map of the universe. That's right. So here's what it is. Here's a framework for a theory of everything. It's just a framework. It doesn't fill in the details. Because we don't really know what the fundamental ontology of our universe is. And we don't really know what the fundamental dynamical laws are yet. But we have an idea about what they'll have to fit in with. Because we know that classical mechanics works very well at a certain level. That quantum field theory, well, it has internal problems with it, but it works quite well, and so on. Also, we know the thermodynamics works really well. In fact, Eddington has a famous quote in which he basically says something like this. If somebody tells you that your favorite fundamental laws of physics are not quite right because they come with an experiment that violates them, say, well, I'll look at that. Too bad for me, maybe it's not right. But if someone comes up and say that they've somehow refuted the laws of thermodynamics, you can just tell them to forget it. It must be wrong. And this has been the experience of physics. As the fundamental dynamical laws have changed, so people thought of different things. The basic ideas of second law of thermodynamics has maintained itself. That the experience with that came up with the development of general relativity and thinking about gravitation, the increase in entropy in the whole history of our universe. The second law survived that, even though the fundamental dynamical has changed. Of course, general relativity isn't the last word there. So what is this mentaculus? Well, it's whatever the fundamental dynamical laws are. It's also a law, or a law-like proposition that says that the universe is macrostate, the early universe, around the time of the Big Bang, what we call the early universe. It was very, very low entropy. As I was telling you before, that was with the picture of Penrose's picture. And what David Albert calls the past hypothesis. And then this probability distribution that Boltzmann introduced, the uniform probability distribution over all the possible microstates that realize this macrostate. Here's a claim that every special science sits on top of this. Every probability claim that's true, that is an objective probability claim, comes from this. Now, of course, for me to defend that would take more than 3 minutes I have left. I've got at least 3 minutes left. So I'm not going to be able to do that, but I want to give an advertisement for it. And then I can sell you things about this later. In fact, I can sell it to you for free, just if you write me emails. Okay, but what is this? How does this connect up with the view about laws and probabilities that I was talking about before? Well, my proposal is that what Lewis calls a best system of the universe, which gives us account of laws and probabilities, is this is what the best system of our universe is. It's empirical, it's contingent. Our universe has a particular history of the positions and momenta of particles, or values of quantum fields, whatever what the fundamental topology is. And the best systematization of all of that is the Mentacula that I just told you about. I have to make some adjustments in the way Lewis is thinking about a best system in order to make this work right. But I don't think I want to go into that right now. But that's the basic idea. What's especially interesting and exciting to me about this idea is that the metaphysical underpinnings of this are pleasing to me. They're relatively light. Laws are not things separate from the events that occur that somehow have to govern the events. You don't have these fundamental powers which make use of some notion of causation, which really we don't think of it, at least physicists don't think of this, we shouldn't think of this as a fundamental. Causation is not something fundamental in our universe. This is something, a point that Russell made a long time ago in his paper about the notion of cause. Russell said, you might remember that, something like, I was talking about this morning, that causation is, Russell wanted to get rid of causation altogether. That we don't want to do, but we don't think it's fundamental. Russell said causation is like the British monarchy. It's mistakenly kept around. It's kept around because we mistakenly think that, like the British monarchy, it doesn't apply. We need the notion of causation, but it's not fundamental. So we don't want that as a fundamental account of metaphysics. So I think the Lewisian account is very nice. Furthermore, Lewis's account is very of probability, and Lewis didn't realize this himself at first. It's completely compatible with the fundamental dynamical laws being deterministic. So what Lewis's account will entail is that for a world like ours, we're in the metaculous world, while the metaculous entails there being lots of conditional probabilities that are completely objective, so the conditional probability, given the Big Bang, of us being in this room, the state of the universe, given the past hypothesis, how likely it is that there'd be a bunch of people looking like us being on a planet like the Earth. There'll be a probability like that that's in the metaculous. It's not telling you how to figure it out, just don't consider that. That's completely compatible, that conditional probability, with the dynamical fundamental laws being deterministic. And one of the big puzzles about the foundations of probability is how they could be really objective probabilities if the fundamental dynamical laws are deterministic. So there's an answer to that through this account. So here's the metaculous vision, the thing I try to sell you. You can get a lot of interesting stuff for philosophers out of this. First of all, it gives an account of laws of thermodynamics. That's how the whole thing started. And it gives an account of things that are not quite the laws of thermodynamics, but are close to it, like Brownian motion. Or for example, if you were to take a pencil and put it on its edge, everybody knows what happens. After a few moments, the pencil will fall over. Well, that's due basically to Brownian motion of the molecules of air. And you can actually do estimations of how long it would take for that to happen. Or here's a nice example that came to my mind while Adrian was giving a talk earlier, because he mentioned with admiration, and I have admiration for her too, but I think her views about these things are completely wrong-headed. He mentioned Nancy Cartwright. So Nancy Cartwright at one point objects to there being fundamental laws that we have reason to think they're fundamental laws which will characterize how a dollar bill will fall, thrown out of a tower. Because she says, look, you throw the dollar bill out and it'll fall different places at different times depending on the temperature and the humidity and the air currents and so on. And that's, she's saying, it's right. But it turns out that the probability distribution, which comes out of the metaculus, comes out of statistical mechanics, will entail a probability distribution. And this can be calculated for how likely it is, depending on the temperature, humidity, and so on, how likely it is the dollar bill will land in this place and that place and that place. And in fact, you get results that agree with the fundamental, in this case, all you need is the classical mechanical laws, which is low enough for this. So that's a nice refutation, I think, for Nancy Cartwright. I've been meaning to write that up for about 20 years, but I haven't gotten around to it all about it. Okay, it does more than that. This account also explains the arrows of time. many people have said that there's a connection between the increase in entropy and the fact that there's a difference between the past and the future. But there's more than that can be extracted out of this probability distribution. We all know that in the future we can make a difference. Small differences in our brain will make for big differences, or can make for big differences later. Some of us more than others. So small differences, let's say in Trump's brain, this is almost as scary as Boltzmann's brain. And in fact, Boltzmann's brains are probably likely to be better ones than Trump's. But I don't mean Boltzmann, the person's brain. This thing called Boltzmann's brain. The small differences in Boltzmann's brain might lead to the end of life on Earth, right? So that can make for big differences in that temporal direction. But it won't make much of a difference in the other temporal direction. Now, in fact, that can be accounted for in terms of this probability distribution and this so-called past hypothesis. And as I said, I think this can account for all of the probabilities. In fact, here's a little picture that may give you a feeling for this. But how many minus minutes do I have? I'm sure I've gone over 5 negative minutes? No, 5 positive minutes, okay. So here's a picture, rough, but it sort of illustrates the idea here. So think of the tubes in this picture as being sort of the macro state of the universe, or any subsystem of the universe. Think of the thin lines as being the microstates. Many possible microstates, infinitely many, literally, compatible with the macro state. The universe starts out at the bottom in this very, very low entropy macro state. And then, depending on exactly which microstate it's in, although the microstates develop deterministically, not probabilistically, the macrostate will develop probabilistically, because different microstates will diverge from each other. Of course, this is well known in statistical mechanics. Sometimes people call this a butterfly effect, but it happens all the time. A small change in one small difference in one place in Africa might cause for a hurricane in Bermuda or something like that. And in fact, that's right. Small micro differences can make for very big macro differences in one temporal direction, the direction we call the future. In fact, that's why it is the future. There's no such thing as the direction of time itself, but there is this directionality in the way events are laid out in our universe that are then captured by the laws. Okay. So you can see the connection between this, I think, and let me say a little bit about this. Let me say this slide first. So think of that M sub 0. That's the past hypothesis microstate, and it has this very tiny entropy, and the universe evolves, becoming more and more complex as entropy increases. And that will continue becoming more and more complex as bodies gravitate to stars and planets and so on. These are complex systems. And under the influence of gravity, in fact, it ultimately heats up the Earth, and forming some stars it makes for nuclear fusion, which will produce the kind of low entropy radiation, which eventually will lead to there being systems on Earth that adapt themselves to harvest the free energy from the sun. And maybe out of that comes life. If I knew the answer to the origin of life, I wouldn't be giving this talk, I'd be giving that talk. But I assume nobody knows really quite enough to say about that in detail that we were in. Okay, so if the universe has an equilibrium state, that's maximum entropy, that's where we're heading. In fact, it's very likely that the universe doesn't have an equilibrium state, that entropy can increase without bound. But that's a question of consciousness for us today. Okay, so this is a probability map of the world, as you can see what the calculus is. One other quick remark, that we named this thing in the calculus, obviously in the spirit of self-mockery. And you can see it's so ambitious that anybody put this forward, which needs to do it with an expression of self-mockery, and that's my feeling. Unfortunately, some people who've written about this didn't really understand that we meant this as self-mockery. And so they pointed out that we should be careful to use a word like this, because the guy who introduced this word is a sort of nerdy guy who never gets out of his pajamas. Anyway, so much for telling stories. This has happened to me now twice with the God story, and so I should be careful. Okay. So I was thinking about this, and I had this on my slide before the talk by Adrian, but if you think about Stephen Gould's question about replaying the tape of life, that sort of can be seen in the tree picture of the probabilistic macroscopic evolution of the world, compatible with the deterministic microscopic evolution of the world. My understanding of what Gould is asking here is go back at some point in this tree. Could go back to the Big Bang, or a little bit after the Big Bang, or back to the formation of galaxies at some point, or back to the formation of this galaxy, or the sun, or the Earth, and then say, how likely is it from this point that life will evolve, or that life with things like human beings will evolve? Here's what makes me feel good, that within the impactments, within these laws, there's an answer to that question. Here's what makes me feel bad. I don't have any idea, nor will anybody have any idea, about how to extract that answer from out of the impactments. Because in order to do that, we would have to know what microstates correspond to the macrostates are that we're interested in. And of course, we can't do that even for fairly simple, small macrostates. We know that they're made to be what they are by some microstates. So there's certain microstates that realize what it is to be a living human being, let's say. It's going to be immensely complicated, but nobody will ever be able to specify them. And of course, anyway, the boundaries are sort of vague anyway. Okay, what about special science laws? Well, if you think about what a special science laws are, there'll be claims like, well, when a system is in macrostate F, it will be later in macrostate G. There might be even a causal connection that's spelled out, and something I didn't say, that my hope is that the concept of causation, or what causation is, can be characterized in terms of the probabilities that come from this, from the calculus. And if you think about it like that, then you realize that, well, what we think of it, when we think of within this calculus picture, when we think about a special science law, they will correspond to things like the probability of G given F and appropriate background conditions, and maybe other conditions that held in the universe earlier will be very high, close to 1. So why is it that all crows are black? That's a law that does when the philosophers of science bandied about when they first heard philosophers of science. Well, because being black, probably being black, given that you're a crow, and appropriate background conditions about crows and other stuff that involved the evolution of crows is very high. Okay, and that probability has to come from the calculus. Now, why am I going so far to think that? I'm not sure I made the argument really translucent here, at least, not really transparent. But the idea is something like this, that, look, thermodynamics is widespread. It applies to everything in the universe. There's tons of evidence for it. We know that thermodynamic systems are built up out of many, many degrees of freedom, atoms, fields, and so on. Boltzmann showed how, by applying the probability distribution over all of that, we can recover the macroscopic laws of thermodynamics. He ran into the reversibility problem. Eddington, Feynman, and Albert later showed how to solve that problem with the low entropy of the early universe. Put it all together, and we now have a probability map of the universe. So all the probabilities come out of that. There's no room for anything else. So when I was sort of pushing Elliot in his talk about what he meant by probability, I wanted to push him in the direction, which I did a little bit in email exchange before in the morning last night, which is why I'm so tired and a little bit hyper right now, that this is where there's no place else for probabilities to come from. And the argument for it is, we have good reason to believe that in the calculus from thermodynamics and the way that statistical mechanics underlies thermodynamics, we have other evidence for it from Brownian motion and from Wright pencils fall over and some other places like that. We can probe this probability distribution. It also does other things that philosophers have been looking for a long time, like giving an account of the directionality of time. and it provides a kind of basis for the special science laws, the probability of the distribution of the special science laws. So to say that this is ambitious and imperialistic is an understatement. But that's sort of the picture. Now, one could go a little bit further and just say something more about how to identify special science laws within this account. And I have a couple of graduate students who are working this out now, and they've come up with some very good ideas. So I'm not going to say anything about this now. But the basic moral is that all of those probabilities that Sober mentioned when he says that biology and evolutionary theory are awash with probabilities, all of them ultimately come from statistical mechanics. So Schrodinger's insight early on, that is, rather than being a conflict between thermodynamics and there being life and the evolution of life and so on, rather than there being a conflict, because there really isn't a conflict for reasons I talked about earlier, but more than that, statistical mechanics is going to hold the key, I think, to giving an account of the origin and the evolution of life, because ultimately it's going to be what's at the bottom of whatever kinds of probabilities occur in evolutionary theory. So, it's not
So, like Barry, I'm not a philosopher of biology, but I wanted to comment on this paper because why not? So, in my commentary, I'll first give a summary of what I take to be the major tenets of Loewer's giant project, and then I will point out what I think is unclear to me and in his proposal, and invite him to clarify certain steps in his project. So, Barry Loewer defends the best system account of laws, according to which laws of a scientific field are true generalizations that are entitled by the best systematization of whole truths expressible in the fundamental vocabulary of that field. A scientifically best system, on his account, is the system that best combines certain scientific virtues like simplicity and informativeness and fit, etc. And in this account, therefore, all laws are parts of a system of laws. Loewer advances a reductionist best system account of laws to explain how macroscopic special science laws, like laws in biology, economics, and psychology, are entailed by the microscopic physical laws. And he believes the version of physicalism is true. On his view, there are fundamental dynamical laws that completely govern, either deterministically or probabilistically, although I should maybe use the word govern, as the evolution of all microphysical events. So there are no additional ontologically independent dynamical or causal special science laws. Or I should say, there are no ontologically independent fundamental special science laws. They are all somehow entailed by physical laws. He believes in what he calls the microphysical completeness thesis. So basically, I'm relying on his works, his papers that he didn't mention here, to kind of give you a general background to point out the significance of this project of Mentaculus, right? The background assumptions of this larger project. So, Loewer thinks that we can understand how special science laws emerge from microphysics, if we understand how thermodynamics is related to fundamental dynamical laws. For this task, we first need to get clear on the differences between the features of special science laws and fundamental laws of physics. As Loewer explains in another paper, special science laws, such as laws of biology, psychology, and economics, typically apply ceteris paribus and are often probabilistic, and they are also temporally directed. Fundamental dynamical laws of physics, on the other hand, are not temporally directed. They are temporally symmetric. Another difference between the special science laws and physical laws is that typical special science laws are causal, while causation doesn't appear in the fundamental laws of physics. Moreover, fundamental dynamical laws are global, meaning that they specify how the global state of an isolated system, such as the universe as a whole, evolves. Special science laws, however, connect relatively local features of systems or a collection of interacting systems. So there are all these differences between special science laws, like biology laws in biology, economics, and psychology, and the fundamental laws of physics. In brief, while fundamental laws of physics are temporally symmetric, then do not mention causation and are global, special science laws are typically temporally asymmetric, causal, and local. As is clear, if one wants to show that special science laws emerge from fundamental laws of physics, one needs to explain the emergence of this temporal asymmetry from temporal symmetric laws. In order to do so, Loewer focuses on the special science of thermodynamics, which is about macroscopic quantities and behaviors such as heat, temperature, entropy, and equilibrium. As he points out, when one wants to account for the second law of thermodynamics, merely in terms of temporal systematic fundamental dynamical laws, and the probability hypothesis, in which a uniform probability distribution is applied to a system in macro conditions, we have a problem. We encounter the reversibility paradox. So we can't really get the second law of thermodynamics purely from fundamental laws of physics and probability hypothesis. That is why Loewer suggests that we should accept David Albert's proposal to take the universe's initial low entropy macrostate into account in order to be able to account for the evolution of the universe and to kind of account for the temporal asymmetry of the second law of thermodynamics. So being inspired by David Albert's proposal for thermodynamics, Loewer thinks that all special science laws are entailed by three hypotheses. First hypothesis is the fundamental dynamical laws. So basically, this is assumed to be either that all microscopic level events are somehow governed by deterministic and temporally symmetric laws. The second hypothesis is the past hypothesis, and it's the boundary condition characterization of the macro state of the universe at a time shortly after or at the time of Big Bang. And finally, the third hypothesis is the statistical postulate, a law specifying a uniform probability distribution over the macro states that realize the initial state of the universe. So these three hypotheses, according to Loewer, provide a kind of probability map of the world, a probability map of the universe, to which he calls calculus. In response to the question of how does the directionality of time emerge from microphysics, unidirectional symmetric laws, Loewer answers, well, it emerges from microphysics together with calculus. Once the dynamical laws are specified, the calculus answers all questions in the form of what is the objective probability of X given Y? In a sense, calculus is a complete scientific theory of the universe, and with the correct dynamical laws, it is the best system of the world. So it is very ambitious and large project, as you can see. So Loewer wants us to take calculus as the best system of the world seriously, his suggestion that it is the best system of the world seriously, and admits that taking it seriously means addressing the questions of interpreting the probabilities posited by the statistical postulate and the past hypothesis as laws of the system. So remember the three hypotheses that constitute the calculus. He kind of thinks that we should take them to be laws or law-like hypotheses. My questions then, given this general kind of background, is how can the past hypothesis be a law or a law-like statement, given that it's just a contingent description of the initial macrostate of the universe. In the best system account, the laws are generalizations entailed by the best system for that world, but the past hypothesis is not entailed by the system. It seems it is rather a precondition or some kind of a priori assumption of the system. My second question is, I think he kind of answered this in the presentation, was Metropolis is an objective probability map of the world. And if determinism is true, should we not conclude that all probabilities are subjective? The third question is about how can we get causal relations that we talk in biology from in special sciences. How can causal relations emerge from Mentaculus? It's not clear to me that you can have an account of causation merely from probabilities. So that's the question I wasn't clear about. And finally, how can one distinguish mere accidental regularities from law-like regularities in terms of probabilities? It seems like Necessitarian accounts of laws of nature have a good answer to this question, the last question. They basically say that, well, law-like regularities have some kind of necessity that accidental generalizations don't, but it seems like we can't really have a room for necessity in the best system account. So these are my questions, basically, and thank you.
So I want to be just very brief. Sandy's questions are excellent, and I can answer 3 of them, but I can't answer 1 of them. That's a work in progress. So the ones I can answer are that the past hypothesis is a law because it qualifies as a law on David Lewis's account of laws. It is part of the system which increases the informativeness of the system enormously. So adding it to the dynamical laws is a simple way of increasing the information about the universe, but not about the microstate. It increases the information about the thermodynamic and the rest of the macrostate. And so that's a jiggle in a change I want to make in Lewis's account. That the goal, the ideal science, which is, if you think of Lewis's account, he's really asking this question. He's just making this proposal. Laws are the certain generalizations or equations which would be entailed by, so to speak, final science. What the best science that could come up, not that we can come up with, the best in principle science that could be. And part of that is that what we want from fundamental physics is that they come along with an account of how the rest of the world, the non-fundamental part, fits in with the fundamental part. And among the parts of that is how certain special sciences, particularly thermodynamics, fits in with the fundamental part. That's already been built in to the way physicists think about proposals for fundamental physics. If anybody made a proposal about fundamental physics that they couldn't understand how thermodynamics fit in, it would be rejected right away. That's what Eddington was basically saying that I mentioned earlier. So the past hypothesis qualifies as a law because it's part of the best system. Now, many people think of laws, they think of dynamical laws. This one is not a dynamical law. It's a specification of a condition. I called it an initial condition as though it's temp time. I'm saying that it held at the first moment. But that's not the right way to think about it. It's rather the right way to think about it is that the universe doesn't have any first moment or last moment in it fundamentally. What it has in it is a distribution of fields or particles or whatever, which have particular boundaries. At one boundary, entropy is very, very small. At another boundary, entropy is very high, maybe equilibrium. And what makes for one time being the past is that the mentaculus can recover, the laws can recover what we mean by the past. The things like that we can make a difference to the future, but not to the past. That we can. I didn't really explain that in detail how that would work. That you have to read some of the stuff that David and I have written to see how that actually works. But another one is that we can have much more information about things in the direction, the temporal direction, towards the low entropy time than in the other direction. So these are what we mean by there being a directionality in time. And I think all of those principles, including our feeling that time passes, because that'll require psychology as well. But I think we can give an account of why we have this feeling that we're so inclined to say that time flows like a river. And still we think for a minute, it flows like a river. Where's it going? It's going away. Where's it going? But you know, how fast is it flowing? And we realize, gee, that doesn't make much sense. So, but we can recover why it is that we have that account. So that's my answer to why it's a law. Like Sonia said, there is something to say about how it is that probabilities can be compatible with determinism. That's one of the great advantages of Lewis's account of probabilities by system account. So I won't say anything more about that. The question, how can causal relations in the special sciences, or just ordinary causal relations, emerge? That's the question I can't answer yet. I have an idea about how to go about answering that. There are ideas around about how to get probabilistic accounts of causation that come from Ellery Ells and Jim Woodward is someone in the neighborhood. Nancy Cartwright, in fact, worked on this problem in a while, though she threw her hands up in the end, though it couldn't be done. And I think it's an interesting project, and it would be great for me if I could figure out how to give a good account that's close enough to what we need of the notion of causation from the probability distribution that comes from the calculus. But I don't know how to do that yet. And how one can distinguish mere accidental regularities from law-like regularities. Well, of course, in the universe, there could be accidents. For example, it might be that some event, coin flipping, someone flips a quarter or something like that. Maybe it's the whole history of quarter flipping has turned out that it's landed, heads 75% of the time, when in fact the main calculus probability might say something different from that. Then it would be an accident. So what the accidents are the divergences from the calculus probability. Actually, there's a really interesting example of that I have to just tell you about. It's an objection that Philip Kitcher makes to the idea that physics can somehow contains within it all the ontological part of the explanatory apparatus of the special science laws, including evolution. Of course, what he brings up is Fisher's law about sex ratios. And he says, look, wouldn't it be just, without there being a law of evolution, the law that Fisher came up with, that that leads to why there is that there are more male births. I forget his example was in London, or some 50-year sequence in London. I guess it goes for any sequence of years. More males, human beings are born than females. And the explanation is that at mating time, there are just about as many males around as females around, because males have a way of reducing their number in various ways before they get to mating time. I guess, I apologize to the biologists. People know about this in the audience. It's a pretty rough statement of this. Okay, so he thinks that that needs to be added as an additional law over and above any law that you get from physics. And I think the reason he thought that is he didn't realize, as most people who are interested in reductionism and physicalism fail to realize, that an important component of any reductionist account would be the probability distribution from statistical mechanics. And the probability of statistical mechanics, better agree with Fisher's law, because if it didn't, there'd be a conflict between statistical mechanics and evolutionary biology, and there just can't be such a conflict. One would have either statistical mechanics would have to be wrong, and I think we have no reason to think that, or there'd be something wrong with Darwinian evolutionary theory, and I don't think we have any reason to think that either. So while no one is in a position of proving that you can extract Fisher's law out of the statistical calculus, it seems to me we have very good reason to think that it can be, so it won't be an accident.
Thank you. So now let's take questions. Here, again.
Okay, let's suppose you are right that if probabilities are objective in the spatial sciences, then they will have to be coming from fundamental physical laws, right? But that's not really helpful to practicing biologists who are interested in figuring out why some traits decrease and why some traits increases in populations. So she has to find a way of answering that question without answering the question how those objective probabilities arise from the fundamental physical laws. And it's a fact that we can't actually calculate those probabilities, at least at the moment, right? So I believe that no biologist will disagree, or philosopher of biology, that if those probabilities are objective, they somehow gotta be coming from fundamental physical laws, but it's not helpful. So philosophers of biologists who are interested in understanding the practice of biology, they are not focusing on those issues, and probably that's why is focusing on how evolutionary biologists figure out to assign fitness values. So they will figure out variations in fitness, and from that they will figure out how trait frequencies changes, right? So epistemologically and methodologically, this ontological claim don't seem to have any significance in terms of the practice of biology. And I agree almost everything you say. If you have empirical laws in the higher level, they will have to come from fundamental physical facts or laws, right? Where else they will come from? So somehow it's got to be that will be ground. But accepting that doesn't help us understand how spatial sciences work, how people do things in those sciences.
I'm totally with you. I agree with everything you said, except that you seem to think that it's the job of philosophers to help biologists, to help special science.
No.
It's the job of philosophers to make trouble for them.
Oh, okay, that's fine, but I thought, I think our job is to understand, this is Eliot's claim actually. He said it somewhere, but I don't remember where he said it. The point is to understand science, not to change it. So, as a philosopher of spatial science, you are trying to understand science, not to change it. Really.
But there's understanding and there's understanding. First of all, I think sometimes philosophers need to make changes, and they've had this effect where, let's say in Foundations of Physics, where I'm quite familiar, physicists have been incredibly dopey about the foundations of quantum mechanics. But this is a whole other story. I don't mean all physicists, Einstein definitely not, but here's a place where physicists, if they really want to talk about the foundations of their subject, really should listen to philosophers. So here's a place where the change is in order. But in general, I agree with Eliot's remark that you were quoting. But there's different kinds of understanding. There's philosophical understanding, which, from my point of view, or at least a part of philosophical understanding, is understanding how, as Wilfrid Sellers puts it at one point, how everything hangs together with everything else. That's what I'm in the business of doing. And I think that the story I'm telling you about is the answer to that. There's something else to do, which, and this is what I had in mind when I was saying about the difference between philosophers of biology, like Adrian and Laura, when they were talking, and they were into the details at one level, and I'm, from the point of view of philosophy of physics, you're far away looking at how everything hangs together. That's what I'm doing. But I don't think there's an incompatibility. However, I do think that there's a question, for me, related to what you were saying, and that is to understand from the mentaculus why it is that the practices in physics, particularly collecting evidence in the way that's actually collected in biology, why it is that the certain frequencies really give good reason to estimate the probabilities that ultimately I think must be the statistical mechanical probabilities in evolutionary theory. So I think that is part of the project that I would have to carry out in order to do this right. But I'm not in the business, which is a very reputable and good business. I wouldn't object to that. I'm on the other side of this thing, from the
I agree that that's an interesting question to follow, but I think the philosophy of spatial science can be done without doing it. That's
sure, of course, it can be done without stressing this.
I don't understand how one can claim to have found the best system. I mean, don't we have severe limitations as human beings? And wouldn't it be you as a theologian, maybe, who can claim there is such a best system? We may only have approximations to it, but then we should grant, for instance, that maybe thermodynamics doesn't figure in the best possible system.
Well, and of course, we can only base what we say on what we think we know now and what's best now. Now, I thought what you were going to say is how can you claim to have the best system since we don't know how to, there's no quantum theory of gravity is basically the way it's usually put now. And that's what I thought you were going to say. And of course, I took care of that by saying we don't know what the fundamental dynamic laws are. The system I'm describing is a sort of framework for a system. I do think that we know enough about our world to be very, very confident that whatever the practice of physics comes up with, thermodynamics will persist in it. There's just too much overwhelming evidence for that. So doubting that and thinking that may not turn out, because that's possible. Who knows, we may discover where David Chalmers, in the brains and fats and matrices, or even Boltzmann brains, which I told you I wouldn't tell you about. That could be the case. I'm not in the business of refuting that kind of skepticism, I can't do that. But I do think we have good reason to believe that. And there's another part of what you said which is very important to my project. I think the notion of law is a creation of human beings. Of course, the concept is, no one would disagree with that, but that what it is to be a law is actually built out of the practice of the history of physics. Now, this is an element of a kind of, I don't know what one might think of as a kind of, in the direction of what someone might think of as a kind of, I don't know, move towards the direction of relativism. I don't think it's a bad relativism, but it would take a long discussion to try to persuade anybody that this is okay. So my own version of the best system account is a bit different from Lewis's, and you don't want to hear a whole other talk about that.
Andrew, drink, and then Laura.
Thanks. So obviously this is quite your project is sort of fairly programmatic, right? It's how it plays out. It's going to turn a lot on, committing to your variations on Lewis's stuff. But I was kind of struck by sort of like the claim you made about the idea that to claim autonomy, you have to admit the idea that the laws of thermodynamics have to be might be false or something like that. I wanted to just put an alternative picture up, which I'm only going to put super sketchily, but I found myself thinking about the sorts of things that Mark Lange says about laws. So he's sort of approximately a sort of coherentist about laws. Lange?
Okay.
Yeah. So he's roughly sort of a coherentist about laws in a certain type of way, and the picture he gives about, say, ecological laws I think is really, really interesting, where he says, look, ecological laws are setting out, let's think of it as sort of a modal space, which contains some physically possible worlds, and some that aren't, right? Which I think is super, really interesting, right? And leads you to think, oh, well, ecologists aren't just interested in what happens in physically possible worlds. They're actually interested in these other worlds, right? I think that's fun. But it led me to think the following sort of thing, well, it might be possible that, on the sort of Lange picture, you've got, think of it as sort of cheesy Venn diagram. You've got the physically possible worlds, and you've got the ecologically, or pick your favorite special science, possible worlds. We, of course, assuming that we've got it approximately true, are in the overlap between those worlds. Which then leads us to sort of another way of thinking about the probability map, right? So your view is the probability map has the roughly emergence. We get the high level stuff, but of course, as you point out, it's not like we can show that. It's very hard to show. What you might say on the sort of Langean sort of picture is, well, obviously they're going to be consistent with one another because we live in the overlap between those two sets of possibilities. But it doesn't follow from that, just because they're consistent, that there's sort of an emergence between them. So I was wondering, I mean, obviously very different programmatically, but I'm kind of interested in what you make of that kind of view.
So let's see, I do think I missed that when you said who you're referring to, it was Lang?
Mark
Yeah,
Lang.
I never know whether.
Mark
do I pronounce
Lang.
his last name?
So you'd be interested to know that he's my cousin. So there's clearly some sort of genetic abnormality. So I think so while we were writing on somewhat similar related things, I think his particular account of laws, this counterfactual account, is terribly screwed up, but that probably doesn't depend on me, what you're saying here. I don't really know about what you're saying there. It does sound like it's a sort of instrumentalist account, the way you're attributing to him, and one which maybe thinking of laws as not characterizing the actual world, but somehow other possible worlds. I don't think there are other possible worlds in that sense. This is where I diverge from Lewis. I think there's the actual world, and other possible worlds are constructs by us for what we learn about the physics of our world. So there is deep philosophical differences. Of course, I'm perfectly fine with arguing for my view and against his view. We've done this in print a little bit. We're actually just second cousins in the genetic and I will tell you in private the story about how he got into philosophy. I don't want to tell the whole audience about this, if you want to hear it later. I think it's fine to develop these alternative pictures. And there's nothing about the picture that I was giving that I think is so secure that it shouldn't be confronted with all sorts of opposing pictures and having learn better by having them interact with each other.
We should move on.
Laura?
So let's imagine we take for granted your picture. And I guess what I'm wondering about is once we could, like we did have this map, and we could spell it out, it was practically possible. So we could sort of tell you which of the probability statement, probabilities in the high-level sciences were like correct, the approximations that scientists have given are correct, objective, and which are wrong. Of those that people are right about, or the laws that the high-level scientists are right about, what kind of explanation of those things could this framework provide? I guess in my very schematic understanding of what it would provide, it would be like you're just carving up these spaces and you're just saying that, you know, in this map carving, there's some probability or some percentage of these states have some other property. And I'm not seeing that as like very explanatory, but I might not sort of grasp how
I think of when we first started saying that, I was thinking that this is very much related to the way I really want to think about laws, which I didn't quite explain when you were connecting it to carving up. I do think that carving up is very much part of the account that I want to give of laws, in the sense that, so here's an amendment I'd make to Lewis's account, but stop me if I'm just going off what you have in mind. That when Lewis takes for granted that there's a fundamental metaphysics or God-given or Lewis-given right way of carving up the fundamental universe, I don't think that that's right. And I think that the carving up comes from the enterprise of doing science, that we want to come up with not just the best systematization, but the best systematization of different carvings up. And the carvings up that we start with comes from the biological and psychological endowment that we start out with. We understand the world in terms of certain kinds of properties, the colors of things, the sizes and shapes of things, that things move around in certain ways is the important one, and so on. And we want to give an account of explaining, but basically science, contemporary science started with giving an account of how things move around. Why do things move? Somebody, I think Democritus already had this idea, but it's clear in Descartes and Newton that what's really important is where things are and how they get there. And that's one of the linchpins of explanation. So we want regularities, laws, that characterize how things move around, because we think we can understand a lot more if we understand how they're moving around and how they get to where you're getting. Is this even connected to what you had in mind?
A little bit. I mean, maybe, so just maybe take like a probabilistic statement in epidemiology. Like that the probability of contracting influenza if you've had the vaccine and you've been exposed to it is 20% or something. So that probability is, yeah, the immunological probability, that's somehow going to come out of the mentaculus. And I'm just wondering what the mentaculus is, whether, I mean, it's going to sort of be readable off it. I'm just wondering whether, when I was imagining like making sense of high-level probabilities, I thought I was going to get an explanation in terms of physics. And I'm just wondering whether, when maybe we can tell you whether the mentaculus, let's assume it can tell you whether this is correct, but can it tell you like why the probability is high it is?
It can go deeper, but let's see. Here's a way, I think this is the way I like to put it, though it'll sound too packed, I think. The way I like to put it is that it's the job of epidemiologists to tell you what epidemiological facts there are, what epidemiological regularities there are. It's the job of physicists to tell you what laws of physics there are. It's the job of philosophers to tell you what laws there are. It's the job of philosophers to tell you what probabilities are. So I think that I'm telling you something about what those probabilities that epidemiologists are invoking, what they really are, both metaphysically in terms of the Lewisian account and physically in terms of the account from statistical mechanics. Now, epidemiologists may go about their business without ever worrying about those questions. Those are questions for philosophers anyway. But every once in a while, an epidemiologist, I don't know, might stick himself with a needle or something like that and start worrying about philosophy questions. In which case, he might find something to what I'm saying. But I don't think, as came up earlier, I don't think that special sciences are enlightened in their practice of the special science by this account.
And Nick was in line, and then, so who's next? Nick.
So it's unclear to me how the mentaculus by itself will enable you to recover all the biological and other probabilities that you want to recover. And the reason is purely technical. So in particular, if there are infinitely many possible microstates that realize the M0 state, and in particular, if there are uncountably infinitely many that realize the M0 state as doesn't seem completely implausible, then at least the traditional laws of probability will only enable you to recover probabilities of macrostates that are really finite subsets of microstates with finite additivity, or if you like countable additivity, you'll get macrostates that are countable sets of the microstates. So that's at the M0 state and also later states. It looks like the initial probability distribution in conjunction with the dynamical laws will only get you probabilities of macrostates that are either finite or countable subsets of macrostates. So it looks like to get all the probabilities that you want to get, you need to also associate some sort of measure with the collection of macrostates, and well, that would be like a fourth component of mentaculus.
Yeah. So we'll have to make some adjustment for additivity. That's right. I agree with that. But of course, this is not going to disturb things very much. Here, all of the macrostates we'll ever be interested in are fairly good sets. They'll be convex sets of, or at least disjunctions of convex sets of microstates, and they'll probably be finite even though there are uncountably many microstates that realize any one of them, there'll be finitely many convex disjunctions of convex states of that sort. Did what I said make sense to you? I didn't say it quite right. So I'm not too worried about that, but I agree that probability mathematics needs to be adjusted in ways I haven't really thought about enough. But maybe you can help me with that.
Yeah, so just real quick, when you say adjustment of probability mathematics, do you mean adopting a different theory of probability that extends the Kolmogorov system, or
yes.
adding, oh, okay.
That's what I mean.
Okay, maybe we can talk later and do that.
So, is that a question here and a question there?
So yesterday, Barry, you were unhappy with the cagey approach to probability that Elliot articulated. And I wonder whether the same charge can be raised against the presentation that you gave today. And in particular, given your willingness to adopt thermodynamic probabilities as irreducible to the dynamic laws and to be added to them, the probability that you identified as the one you wanted to endorse was a notion which satisfies the Loewer axioms, but about which we can say no more than that it systematizes all of the Humean mosaic that Lewis's worlds consist in. Are you prepared to tell us a little bit more about that thing, besides that it is an operator that begins with the letter P?
Well, first of all, telling you that it's the best part of the best, the probability claims are entailed by the best systematization of the world, is telling you a lot. As soon as I filled in details about best systematization.
I thought it was added to the dynamic rules.
But it's part of the best systematization. So it is added to the dynamic. So that it's right that Lewis thought of as the best systematization as just producing the dynamic laws. I'm adding to Lewis that also there's a probabilistic claim. Okay. Of course, it might turn out that the thermodynamic probabilities come from the dynamical laws. That's a possibility that's been, I know you know about this, that's been brooded about in foundations of quantum mechanics. But I don't want to rest anything on that. So I think there are two things we know about probability. One is we definitely know about it. Whatever probability is, it should be related to what we think of as the rational degrees of belief to have. Al Hayek puts that by a nice little statement that says this. He has a little, like, analogy thing, like on SAT tests. His thing is, truth is to degree of belief as, belief is to truth as degree of belief is to what? And he didn't understand this until he and I interacted in quite the right way. He answered chance, but now he knows it's the right answer is the metaculous probabilities. I think he accepted this, okay? So I do think we know this, but forget about that part, about the metaculous probabilities. It's just the idea that one of the things about what probability is, it's a guide to belief, this Bishop-Butler idea. So we know that about probability. Lewis is making a proposal about, given the fundamental ontology of our world, what more can we say about probability? Well, we can say its probability claims are entailed by the best systematization of it. That's saying a lot about the world. It's close to an actual frequency account in the sense that actual frequencies will make a big difference. But it's not an actual frequency account because, first of all, it operates only at certain levels, the fundamental level or the thermodynamic level. And the actual probabilities can diverge, Lewis probabilities can diverge from actual frequencies a lot. And for that matter, Al Hayek has a paper pointing out 15 things that are wrong with actual frequency accounts. So I'm glad it's not an actual frequency account. So I think it's not right. I don't think that the objection I was making to Elliot, that he was happy with not saying anything more about probability, applies here. I think there are two important things to say. One, that he probably would want to say too, that it has to be a guide to belief. But he hasn't told us what it is about probability that it should guide belief. I think that Lewis's account does say something. Now, filling it in to understand what it says is a difficult project, and there are a lot of people in the formal epistemology literature, 10 people, who are working on this. Lewis himself says about his account something like this, that where propensity accounts, those are like the governing accounts of laws, he thinks those are hopeless to understand why they should guide your degree of belief. Lewis says that he can see dimly but well enough, while his notion of probability should guide belief. If Lewis sees something dimly, I think I can't see it at all, but I just trust that he sees something. But I'm working on that problem. It's one of my problems.
So let's start. Thank our speaker.